Okay. Can anyone hear? Can everyone hear me? Even in the back? Is this on? Yeah. Just ahead. Oh, okay. Perfect. Great. So my name is Luka Jacobowitz. This is Lambda World 2018. I'm really overwhelmed with all of you showing up here. Holy shit! It's like, okay. My talk is about testing and testing in the world of functional programming. Very quick about me. I work at Codecentric in Düsseldorf, Germany. Also co-organized some of the meetups there. Shout out to Scala Dus and Idris Dus. If you're ever in Düsseldorf and want to give a talk on Scala, please email me or contact me. I also maintain a bunch of type level libraries, as you maybe can see by my T-shirt as well. Cats, a lot of cats libraries. I also like cats, not just the libraries, but also the animals. And I also maintain this cool library called Outwatch. Furthermore, I am really enthusiastic about FP and functional programming, which is the same thing. But this is why I try to answer some of the more fundamental questions of how do we do FP, and testing is or at least should be a large part of that. So quick preface. We're just going to talk about two things here in a broader sense, and those are property-based testing and mocking. And mocking, not in the Java world, but like in the more functional programming world. And then I'm going to try to present some conclusions. And also, a lot of this talk is going to be kind of opinionated in a lot of senses. So I don't think you have to take everything I say here as completely at face value. There's a lot of things that personally help me in using and writing tests that give me confidence in my code, but they might not equally apply to every single one of you. So just want to have said that. So, okay, without further ado, let's talk about property-based testing. And I think property-based testing is a really, really great way to write tests because it allows us to generate data for our test cases. And that, in essence, allows us to basically get rid of the bias we might have when we manually input data into our functions to test them, right? And so we can no longer basically cheat. We can't just say, oh, this works for this type of data, so all the tests pass, and hey, because that's obviously not what we want. We want to handle edge cases, and property-based testing gives us that very easily. And of course, because of that, because you can't cheat, that means that usually when you write a function and it doesn't handle the edge cases, that means we see, oh, it doesn't work, and then we can't, our tests don't pass, and then maybe we found a bug in the implementation, and we need to change the implementation before we even think about going to production. So property-based testing is great, and it allows us to find bugs before we even do anything at all. So, but property-based testing also has a few problems, I think, in the usage aspect. At least the libraries that we use in Scala. I'm mostly going to talk about scala-check because scala-check is the most common library for property-based testing in Scala. But there are tons of other libraries in other languages that do this differently, especially in dynamically typed languages. But in statically typed languages, this is sort of what I come up with. So let's say we have this function. It's called UUID created after. And UUIDs, they have like a built-in timestamp somewhere. And what this function does, it basically compares that timestamp of the UUID to a date. And of course, what we do is we just say, hey, this UUID is a string, and then this date is a string. And then what we say is, oh, this UUID should use UUID v1 in the comment, and then the date should have this kind of format. But now I want to test this using property-based testing. And if you just say, oh, I just want you do this for any two strings, obviously this is not going to work, right? Because the strings are just going to create some random strings. And even if it creates 1,000 strings, there's a very, very, very low chance that it's going to create a valid UUID v1 and also a valid date in that format. So this is a problem, and I think this is this is a problem that comes up a lot because we have this code, but we know how to test it manually, but we don't know how to basically write tests that do this automatically. So what can we do? The one thing I can think of is that instead of taking two strings, this function, maybe we should change this function. So what happens if we give this function an invalid UUID or an invalid date in that format? So what could happen is, hey, maybe it throws an exception. That's usually not what we want. If we want to write idiomatic, pure, or referentially transparent Scala, maybe it just returns false because it's like, I guess the UUID you passed was not created after. There are different things you could think of, but usually this is not what we want. We want to be precise. And so maybe we shouldn't take two strings. Maybe we should take something else because, of course, the arbitrary type class instance for string is is defined already, and it generates random strings, and it doesn't generate random UUIDs. So maybe we need a different type. And what we can do is we can new type it. And new typing is basically a pattern where we create a new type that is based on another type, and it should be basically able to convert from one to the other. So what we could say, instead of having a string, we could say a UUID is a new type over string that has these specific properties, and the arbitrary instance for UUID is then going to only create valid UUID strings, and same for date, for example. This is something we can do. So, but there are also some common drawbacks. This is very specific to Scala. But some of the things I hear when I say, hey, why don't you just new type it? Well, they say like something like, oh, I won't support the operations I need. So for example, if I have a new type, maybe a euro, a new type euros that is a new type over integer, then I no longer can say euro, the first value of euro plus the second value of euro minus the third value of euro. So I kind of lose like the operations because it's a new type. I can't reuse the functions that that are already available for something like int. So okay, and that means in essence that, hey, if I want to use these functions, I need to convert to and from the underlying type all of the time. And that can be pretty boilerplate heavy and annoying, and it can lead to frustration, things we don't want. And another thing, especially in Scala, is that if you use the value classes, if you extend anyval, which can be seen as a form of new typing, it can give us a performance penalty because whenever you, for example, put a euro, that is an anyval class, into something like a list or a future where it needs a reference type, it will actually have to box that and unbox it again at the end. Because at runtime, the class of something like euro, where it's an anyval, is going to be euro instead of the integer, the underlying integer. So maybe there's some ways around these problems. And one such way can be this new library, well, it's newish library called scala-newtype. It uses a macro and it allows us to write code like this. So we have an @newtype annotation, and then we just say case class euros and int. And if you want to add specific functions to this euro class, we can just add the braces and add functions there. So for example, if you wanted to say like convert to dollars or whatever, we could just write a curly brace def convert to dollars, and that would work. But also what we can do is it gives us this feature called type class derivation. And in essence, what that means is that if int has an instance for a type class, euros can automatically derive that instance. So let's say we have a numeric instance for int, which we do. Int is a numeric type. That means we can also have a numeric instance for euros, because of course the scala-newtype library just gives us this power. So all we have to do is say equals deriving, and then it will just magically work. And what that allows us to do is to write code like this. And so the only thing you need is these 4 or 5 lines of code, and then you can create this line right there and say, hey, okay, I don't need this boilerplate conversions. I don't need to say euros 25 to int plus euros 10 to int minus euros 5 to int, and then wrap that in euros again. So this kind of takes away the boilerplate. And also what it does is it takes away the performance penalty, right? So this macro uses, this macro just completely never boxes. So the runtime type of euros will actually be integer. So that's cool. Another thing you can do is sometimes you want to have specific predicates, right, for a specific type. So not every string is a valid UUID. So what can we do? So there's this small library called Refined, which has been around for a long time. And basically, what it allows us to do is write code like this. So this val URL is a string refined to a URL. So what we can do is say, hey, this is not just a string. This is the refined string that is also a URL in some sense. And what this actually does is it will check the literal and parse it and see if it fits this URL refinement. So if we were, and because this URL is a valid URL, that means that this will just work. But if we try to do this with something invalid, like HRRP, which is not a known protocol, then it will fail at compile time. And we can kind of like get these extra benefits from just adding the refinement to our type. So if we have a string refined URL, then we always know I can do certain things with it. For example, if we have a string refined UUID, that means that I can always read the timestamp out of it, and I don't have to worry that the string is formatted correctly. And of course, this works for literals, but if you had actually runtime values like user input or stuff you parsed from JSON, then of course, you can't just parse it into a string refined URL, and what you do instead is you get an either. So either it is a valid URL or it is a non-valid URL, and then you'll get like an error message, of course, but completely at compile time, which is the important part. And it also allows us to do things like this with numeric things. So we can say, hey, I want an int that is trying to be positive. And this comes in really handy. We use this a lot at work because we have to create a lot of averages over a lot of different things, over different metrics. And what we do is we basically have to divide by things. And dividing always comes with a cost that, hey, this integer may be 0. So if it's 0, it's going to throw an exception. And then I have to like maybe catch this somewhere. And it kind of gets annoying. So what we actually do is whenever we get an integer, we try to refine it as a positive integer. And then we can use a safe division operator. And that basically gives us the confidence that our code is never going to fail with a division by 0 error. And that's pretty cool. So, and what this really helps us with is writing property-based tests. Because now I can, with just the simple import, which says that, hey, I want all of the arbitraries for the refined types, I can, for example, write code like this that says, hey, I have a left pad. And of course, if I want to pad a string, it makes no sense to pad a string with negative spaces, right? That makes no sense. So what we want is a positive integer. And then we can just write a property that says, for any string and any positive integer, if I get the length of the padded string with that integer, it should be at least equal to that integer, right? And this just works, right? This is valid code, and this will just compile and run, and will give you the ability to have these property-based tests based on refined types. So this is really cool. I really recommend checking it out. So the takeaway here is that accepting only valid inputs for your functions make your code, not only makes your code more precise, but also allows for much easier property-based testing because you have a guarantee that generated data will always fit your function. And that is really cool. And there's a lot more cool things out there. So for example, sometimes we have like a bunch of lists, and we want to basically get an average value of that list. And if you look at the length method of a list, it will return an integer. So an integer represents numbers from -2 million to 2 million, 2 billion, I don't know, -2 to plus that size. So it represents a very large range, which doesn't really make sense if you think about it, because a list can only have a length of unsigned integers, right? So it can be either 0 or 5 million or 2 million or whatever, but it can't be anything like -7. It doesn't make sense for a list to have a length of -7. And what that means essentially is that the type is very imprecise. And what we do is we have this thing called non-empty list in cats. Who has heard of non-empty list? Oh, that's a ton of people. Wow, you guys are cool. With non-empty list, you're guaranteed to basically have a positive integer that is not 0, a non-zero integer. But of course, if you look at the length field, even on cat's non-empty list, you're just going to get an integer again. And what you can do with refined is say that, hey, if I have a non-empty list, I want to get its actual size, which precisely has to be an int refined positive. And so refined adds this method called refined size, and it gives you an int refined positive. And there's also tons of other really cool like small things that really improve the quality of life when working with these things. So another example I have is that I told you that when you validate one-time values, you usually get an either. But if you want, you can also get a validated NEL. And that means that if you have a bunch, like a list of strings that you want to validate and turn them into refined types, you can just say, hey, I want to validate all of these using a validated NEL, then traverse that, and then you will get either a list of errors or a non-empty list of errors or a list of valid refined values. And that's pretty cool. So I tried to come up with like a few more examples of maybe how you might not want to use primitive types and use other types instead. Because there are lots of libraries out there that already do this. So if you have a duration of time, don't use int, use something like finite duration, which is in the Scala standard library. If you have something like a non-empty sequence, use that and use non-empty list instead of the standard list. If you have a date, use Java 8's local date, which is really great in my opinion, instead of string. And basically try to avoid modeling your functions with primitive types because they are imprecise, and if you want to use property-based testing, these imprecise types might actually come back to hurt you. For something like an IP address, there's, for example, a refinement in refined that gives you that can refine a string to be a valid IPv4 or IPv6. It's really nice. There's really lots of different examples here, and there's also a couple of other great libraries that I wanted to just show you real quick. Not show you, but just tell you about. And one is Libra, which is like a dimensional analysis, and that means that you get like units of measure. So for example, if you have like, you want to have some kind of length, and you also want to create maybe you want to multiply two values of meters, and then you get something like a square meter. And if you multiply that with another meter, you get a cubic meter. So it is aware of its own dimensions, and that's pretty cool. Another thing that we use is the FUUID library, which is basically a wrapper around the Java UUID, but adds a bunch of functional stuff. Like if you want to create a new UUID, that's going to be wrapped in I/O because it uses like some random number generation. which is not referentially transparent. And then, of course, if you want to create from string, it's not just going to say, hey, yeah, of course you can do that. Instead of it's going to say, hey, I will return an either for you. And then, of course, there's also squants, which is also a type level library. And it's very similar to Libra, but it comes with a lot of different extra built-in measure of units, such as kilowatts and tons. And something really cool that I think is like, hey, how can I, if you have like, maybe you want to create like an invoice for some electricity company or something, and then you can say, I want to divide kilowatts times hours divided by money, and then you can say, hey, this amount of kilowatt hours costs this much money, and then you have an actual value, a type that represents exactly that, and that's pretty cool, in my opinion. So this is basically it about new typing and property-based testing. Property-based testing is super cool. The next thing I'm going to talk about is mocking, functional mocking. And it all comes down to like code like this. So this is non-pure code, but it kind of demonstrates the problem fairly well. So we have the send_xml function, which takes a string and returns a unit, does some kind of side effect, no clue what it does. And then we want to send like a bunch of things, I guess. So we have a list of strings, and what it's going to do is it's going to say, hey, for each element in that list, use the send_xml function to do some side effect. And so what we should have learned from the last section of the talk is that we should split it up. So we should first take that string and parse it into XML, and now we have a function that we can test fairly well, right? So parsing is something we can test fairly well. And then we also have this impure part, send_xml, where we just take an XML and then return an IO of unit. And to recreate the functionality we had before, we have a string and return unit. This time we return IO unit. We just combine these two functions by lifting the either into IO and then flat mapping the two values. So that's fairly straightforward. And then, of course, if we have a list of things, we can use the traverse function to do this for all of them. But it highlights something that I think is a difficulty. So I said that you can test the first value, but how can we test like the sending? So we have this send_xml and it returns an IO unit. This is, in my opinion, really difficult to test, and that is just because testing side effects is hard. It's really hard. So it's like, I don't know what it is, but we can like kind of approximate this. So the difficulty, I think, that comes from testing side effects comes from testing the outside world, right? So we usually like classify our own system as being this pure machine where we can compute pure values. And anytime we leave this system, we have to use something like IO to basically stay within the referential transparency that we want. And that means that anytime we have to leave our own world, it is going to be difficult to test because the outside world is non-deterministic. We have no clue what goes on there. We have no guarantees. And yeah, that makes it really difficult. So the problem is we have to test things that we have no control over, like some external services. If we had control over, we could just put them inside of our application and say, hey, okay, let's test this. And for this, we have two options that are non-mutually exclusive, and I actually recommend doing both. And the first is like the wisdom, the things you would usually hear people say. And I think it applies as well. And that is to use integration tests to just check if the behavior, like the whole behavior of your application, does exactly what we want it to do. And that can be difficult, and can be difficult for a couple of factors. And that can be difficult because if our whole application, if we test our whole application, we basically treat it as one big black box. And that means that we no longer have fine-grained control over what we test. We just test the whole thing. And it's very, very difficult to integration test small parts of our application. And another thing that I find also is that if you want to test a system that's in production, usually you don't want to run your integration tests on the same environment that is your production environment, because maybe it might break something. You don't really know what's going on there. But if you have your own testing environment, basically now you have to say that the testing environment has to be pretty much exactly the same as the production environment, because if it's not, something that might work in test might fail in production. And you don't really have a guarantee that these two things are the same. So integration testing is difficult. I still think it's definitely worth the trouble, and you should obviously do it. But there's also another option that can give you some more control back. And that is to mock the outside world and then test the expectations inside your own system. So never leaving your own system, and just staying in your world and testing the things you do have control over. And that is easier, but it can be potentially less accurate because you're not actually accessing the system. Okay, so how do we use mocking the test I/O? Let's say there's two words, tagless and final. So who has heard of this tagless final concept before? Wow, that's a lot. Okay, excellent. So tagless final, real quick, it basically allows us to write programs that only use like a problem description and don't like get bogged down with all of the implementation details. We have basically very clear separation of description and solution. Sorry. And what we can do is that we can define our own algebras that then basically allow us to define interactions with the outside world. And that means, in essence, we get to work at like an extra level of abstraction where we just have our own algebras to work with, but also maintain flexibility. And we maintain flexibility by saying, because we have separated these two properties, we can say that, hey, I can create a program and then interpret it into something that is going to run the system in production. But I can also say, hey, I can create an interpreter that runs this program with these algebras in something like a testing environment without having to leave the system boundary. And how do you do that? In specific to Scala, real quick, what we do is we model our algebras as traits, usually parameterized with something like a type constructor, where we say where we specify the context in which we want these effects to happen, and then we write programs by writing our programs and then defining the amount of power we need to constrain that type parameter, that context we were talking about. So if, for example, I want to write some sequential code, I can use a monad. If I want to write things that doesn't have to be sequential, doesn't depend on one another, it's just independent computation, I can use something like applicative. Yeah, and then to write interpreters, the only thing we need to do is write an implementation for these traits. That's kind of abstract. I have a whole talk on how to do tagless final, but that's 40 minutes in itself. So I'm sorry if this doesn't make sense yet. But let's look at an example. So we have this function where maybe we're like a hotel service provider and we want to allow our customers to book things. And we have this function, book things. It returns the IO unit. It books a Coke. It books some room service, and it also books a really nice whole wheat hummus sandwich. So this is an example of the code, how it looks before, and now we can try to translate that into tagless final code. So what we do is we write an algebra for booking things, right? And that we call this a booking service, and we use an abstract type constructor f. And then we say, if I want to book a drink, I'm going to take a beverage, and then I'm going to return an f of unit. If I want to book some room service, I'm just going to return f of unit. If I want to book a sandwich, I need a dough parameter and a topping parameter. Sorry, and then I'm going to return f of unit. And if we wanted to write an interpreter for I/O, it's fairly straightforward because we already have these functions that return IO of unit for all of these 3 functions. So now we have to recreate our program using this style. And what we do is we say we require a booking service of an abstract f, and then we say that f needs to be at least apply. And the apply type class is basically like applicative without pure, in case you didn't know. And if we look at the program, actually, this doesn't actually need monad, even though it uses the for comprehension. But because it never actually uses the values that come back, because they're all unit, we can just use apply to basically say, hey, run this, then run that, and then run that. And that's exactly what we're going to do. So we say, hey, book a Coke, and then use this right shark operator that you can kind of read as and then. Book a drink, a Coke, book some room service, and then book that nice whole wheat hummus sandwich. And this code, if we want it with I/O, is going to be exactly equivalent to the program we saw before. OK, and now we can define a possible test interpreter. And to do so, we need to think about what we're testing here and what could we possibly do. So let's have a look here again. So we book some Coke, we book some room service, and we book a sandwich. There's nothing really we can test in the sense that if we return something like ID of unit, right, that's just going to give us a unit value, and we can't do anything with that. So what we do instead is we maybe want to test like the internal wiring and the ordering of these different kinds of effects that happen here. So what we know is that first we want to book a drink, then we want to book some room service, and then the sandwich. And so there is some ordering going on here, and that is something we can test. And that is something that makes sense to test. So what we do is, what we want is basically, hey, given this program, return to me a list, an ordered list that returns the things we wanted to order in exactly that order. And to do so, we need to actually create values for these different bookings. So we have a seal trade booking, and then we have a case for booking a drink, which is a beverage, takes a beverage, and then is a booking. A room service, which is a case object, and then also a sandwich where we need a dough and a topping. What we then can do is use this const data type, which basically says that I have 2 type parameters, and I'm only going to save 1. So a const of list of booking is always a list of booking, and the second type parameter doesn't really matter. So if we look at the book drink function, which is one of the implementations here, it's going to return a const of list booking and unit. But to create it, all we need to do is call the const constructor over a list of drink booking, which is, of course, a booking. And then that just works. And we can do the same thing for room service and sandwich. And now we have a functional service that we can actually call. So to do so, we just say, hey, let's run our book things with the test service. And that gives us a const of list booking and unit. And then we just get the constant out to get that list of booking. And now that is going to have the exact order we want. And what we can do then is we write a list of things that we expect. And then we can assert things. So this is like the long form way of testing how we have these orderings and how the internal wiring is working. So we're not actually testing the external system here, right? Because we don't ever leave our own system boundary. We're only testing the internal wiring of our system, and that is something that can be very important. In this example, maybe not, but in more complex examples where you call first this service, then that service, and then you might call another service, and then you extract the values from here, and then you end up with this large, very large for comprehension, usually. And the only test you have for this for comprehension is the integration test. And so this test gives you, this kind of testing can give you more confidence in that. So, but this was kind of too easy because all the effects were just returning unit. So we were only doing things. But what about having like real stateful external services where we get things out of the service, we also input things into the service, and they have like this internal state that that does something that we can't really see. And that makes it much harder to mock. So we need to ask ourselves two questions. And first one is, what does that external service provide to you? Is it just data? Because if it's just data, if you're just reading data, constant data from somewhere, then we can easily mock that by just creating our own test data. But if it's also something like state, we need to think about how we do that. And what we can do is we can try to mimic the behavior of the external service. And to do that, we might try to write a self-contained state machine within our own system boundaries that is going to somewhat approximate the external service. And that only works if the external service is not extremely, extremely complicated, and you don't want to write a huge state machine that basically re-implements the external service. You just want to write something that approximates it. And yeah, so let's look at a more complex example, something that might actually resemble real-life code. So let's say we're like running a web shop, and we have things like customers, we have items, we have discounts, and we have this function discount all that is basically that basically allows us to give a discount to all of our customers and then return those customers. So what we do is this function takes a discount type, and then what it will do, if we look at this code, is it will get all of the customers from some external service, maybe like a customer database. Then it will log all of these customers, because that's what we usually do. Then we try to get the discount, like the current discount. This might change hourly or whatever. We get the current discount from some external service, and we give it the discount type. That gives us a discount. Then we log that. And then what we do is we take the customers we get and try to update them. And this update discount, if eligible, is going to take a discount and a customer. And if it's eligible, it's going to return an updated customer. And if it's not, it's just going to return the same customer. And then this updated is going to give us a new list of customers that we're then going to log and return at the end. So this is more complex, and it does a lot of things. And the first thing we have to do is turn this into Tagless Final. So we create a logging algebra that's just going to be able to log customers and log discounts with the discount types. And then we're also going to create this customer service. And this customer service has the three functions that we saw earlier, but parameterized by f instead of io. And the get all customers just gives us a list of customer. The get discount, for any discount type we give it, it's going to return a discount. And the update discount, if eligible, will need a customer and a discount, and then it will apply that discount if the customer is eligible, and then return the customer. So those are the two algebras. Next, we're going to recreate the method using those two algebras. And actually, this code looks more or less the same. The only thing we did was say, hey, this get all customers uses the customer service f, and the logging uses logging L. And yeah, this should look basically the same. I'm not going to go through it again. So now what we need to do is we need to actually mock the customer service. And for that, we basically need to determine in our own system if a customer is eligible for a specific discount. And to do so, we need to write our own function is eligible. And we also need to basically update a customer. This should say update customer instead of update discount. I'm so sorry. But we need to update a customer with a specific discount and get a new customer. And these are things we basically replicate from the external service inside our own system boundary to get a better grasp of the test. And also what we want to do is basically hold the state that the mocked service has. And to do so, what we use is just a list of customers and a map that will give you a discount every time you give it a discount type, right? So for every discount type, you get back a discount. So this is just the service state of the mocked service. And now what we can do is we can actually interpret this into the state monad. So how many people know about the state data type in cats? Wow, you guys are really awesome. It's cool. OK, it's great because I don't think we have that much time. So this is basically, this is very simple, even though it might not look that way. Basically what we do is we write an interpreter for a state of service state, where the service state is the case class we saw just now. And then the get all customers and get discount, all it's going to do is going to just take the service state and then get the customers out of there. And then we're going to get a list of customers. And for the discount, we're going to take the discount map and then apply it to the discount type to get back the discount. And then the update discount if eligible is actually going to call the functions that we just talked about, but it didn't fit on this slide, so I made a new slide. And that is here. And this looks a bit crazy and a lot of things at once. So what we do is we create a new state, and we take a discount and a customer, and we check if the discount is eligible, if the customer is eligible for the discount, right? That's what this function does. And if it does, we can update the customer, even though it says update discount. We want to update the customer with that discount. So this val updated is going to be the updated customer. And then what we want to do is we want to get the customers from the current state and filter out the current customer, because we're going to add it back in. So what we do is we filter them, and then we copy it and set the customers to the without customer and prepend the updated customer at the beginning. And we also return the updated, because this function returns a customer. So we basically modify the state of the state monad. And of course, if it's not eligible, we just return the state unchanged and the customer unchanged. Make sense, kind of? Yeah? Awesome. Cool. So now what we can do is we can write a property to basically test all of this. And we want to say for every list of customers, for every item, if we use a fixed discount, which we can see in this first line, discount fix of 20%, so maybe all of our customers get 20% off, then it should be the same if we take all the customers, use this as eligible function, and then fold map using the price for the item. That's going to give us the price for all of the eligible customers. If we then discount this price using the 20% off, that should be the same as running the state machine to get the expected result, using the actual machinery of our code, but just interpreted using an internal mocked state machine instead of the external service. And to do that, we need to run the discount all function using the discount type fix, which is the discount type it needs. And then we also have to give it the test interpreter we gave it. And it's also going to need a logger, where we're just going to give it a logger where basically all it does is do nothing, because we don't care about the logs in this. We could also write a function that tests the logs, but this function is only going to care about the state. And then we also need to provide an initial state for our mock service, which we're just going to give the customers, and then a map. Because we only use one discount type, we only use the fixed discount, we're just going to map the fixed discount type to the discount of 20% we created up there. And then to get the price, all we need to do is use that state monad, run it, and then this run a function, what it does is it discards the state at the end and just gives us back the value of the state. So this state run a of service state customers dot value is just going to give us a list of customers, and then we fold map that using the price for the item, and then we again get back the price, which we can then compare. And this is a property that we can fully test with any number of customers and any item, and this should just work. Yeah, and that is basically how we can mock these external services and put them into our own system boundary. So a quick recap. Whenever the situation allows it, we can try to mock the behavior of an external service, and we can then make it completely deterministic because we have full control over it, and we no longer need to depend on some things that we don't see. And Sometimes this is, of course, completely infeasible because the external service does so many things at once, and it might not be worth doing. You might be better off just creating more integration tests and trying to create better integration tests. But if done right, and if done correctly and in a good way, this can give us more confidence in our testing, because a lot of these internal wirings are pretty prone to have like very small mistakes that might not show up until later. So, in conclusion, try to separate effectful code from pure code. Make use of total functions with well-defined inputs as often as possible. And if you have to test side effects, which you usually do, don't test the external service because someone's already written that and tested that. But try to mock it somehow and see if you can get by with creating your own behavior that mimics it in some way. Yeah, and that's my talk. Thanks a lot for listening. You can